So where we left off last time was talking about, like, we jumped on to Fibonacci, but the reason I'm going to talk about Fibonacci isn't so much because the sequence is overly important for us right now. Although, don't get me wrong, it's a very interesting and important sequence of numbers. We were talking about in the context of computational complexity. Because with iterative analysis, the trick is to look for the loops. Ultimately, it's the amount of time the work's going to get done. But like here we see, okay, there's a loop that's going to run n times. The thing inside of it being run is constant time. So constant time, time n, this is order n. It's linear. But with recursion, we don't see the loops. So how on earth do you determine its computational complexity? And the trick is, well, how many times is the code getting run? This is a function call. So the recursive method is calling itself. So for every recursive factorial method called, a new one is made. And if we're starting at n, we're decreasing n by 1 every time we make a call, and the base case is 0, what's the computational complexity? Well, okay, let's think about this. If we, where's that table? The first time, okay, with the n, then n minus 1, then n minus 2, then 2, then 1, then 0. Okay, so, I mean, okay, it goes to n plus 1 because I guess n to 1. But it looks like this, like, there's going to be a total of n function calls. And each function is linear time. I mean, except for the recursive part, of course. So it's like each function is constant time, except the function call, of course, which is another constant time thing. But there's a lot of them. So how many are going to run in total? Well, n of them. So if each one calls another one, and that happens n times, it's linear. It's happening n times. It's order n. It might not feel overly intuitive, but it might be because you're trying really hard to find a trick to it, but it's just, if I call this with the number 8, how many times is this going to run? 8, well, I guess 9, because that time when it gets down to 0. We could say when this equals 1, return 1, because it'll be the same for Fibonacci. So if n is 8, I will call recursive factorial for 8, 7, 6, 5, 4, 3, 2, 1. That's 8 things. If n is 100, well, I'll do it for 100, 99, 98, 97, 96, 95, 94, and 3, 2, 1. So 100 things. If n is a billion, well, it'll be a billion thing. If n is n things, how many will there be? N. So it's linear. So the trick is, how much work is each function, and how many times is that function getting called? Any questions about that? Make sure I'm recording and everything. Yeah. Did Bilbo just show up to test me? Oh, Bilbo number 2. Okay, good. So yeah, that's the computational complexity. Are there really no questions about this? You all are being pretty quiet. Semester's almost over, but we're not quite there yet. Let's finish strong here. Course definitely doesn't get easier. So just make sure you're on top of this. All right, I'll assume everyone's doing just fine. Okay. Iterative. In fact, okay, did I hear a boop? I did not hear a boop. I'm itching so hard for someone to ask the question, I'm hearing things. All right. Fibonacci numbers. You start with 0 and 1, and then to generate the next number, you add like the current and previous together. So 0, 1, okay. 0 plus 1 is 1. Current is 1, previous is 1, next is 2. Current is 2, previous is 1, next is 3. Current is 3, previous is 2, next is 5 then. Current is 5, previous was 3, therefore next is 8. Current is 8, previous was 5, therefore next is 13. and so on. And you could just keep doing this forever. And this series has interesting properties. But yeah, to generate, start with 0 and 1, and then to get the subsequent number, add the preceding two together. Take a moment and think about how you would write an iterative method to generate these numbers. And again, here's my implementation, and it'll work. But make sure you take your time to understand it just to be safe. What we'll do is we say, okay, previous starts at 0, current starts at 1. Okay, if I say if n is 0, return 0. Yes, I see. So, if n is 0, return 0. Okay, that's the 0th Fibonacci number. Let's see what happens when n is 1. Okay, n is 1. Previous is 0, current is 1, next is 0. I starts at 2. If I is less than or equal to 2 to 1, well, 2 is never less than or equal than 1, so we never run this for loop. Therefore, we just return current. And that is the 1th Fibonacci number. Now, let's see what happens if it's 2. Okay, it's not 0. Previous is 0, current is 1, pardon me. Next is 0, I is 2, I is less than or equal to 2. Well, 2 is less than or equal to 2, so we execute this once. Next becomes previous plus current, so 1 plus 0. Next becomes 1. Now we need to update current and previous. So the previous is now what current was. Current is what next is. So we've just like moved ourselves along. We calculated next and then made it the current. It's like we said, okay, 0 plus 1, that's 1. Okay, great, because this 1 was current, 0 was previous. Added them together, we made next 1. And then we immediately said, okay, current, you are now what next is, and previous, you are what current was. That's all. Did you just say onth? I'm not sure. Oeth? Nth? I'm not sure what you mean. Maybe I did? I don't know. First? Oneth? Sure, yeah, oneth. And then this will, of course, work for every number greater than 2. So if we put in like 10, okay, so 0, 1, 0. 2 is less than 10. So next is 0 plus 1, well, not 1. Then we move everyone down. And so on and so on and so on. So when you look at this, what is the computational complexity of this iterative Fibonacci? Okay? And I'm hearing a lot of boops. My audio cut out at that point, but I'm guessing you said nth, and I was just misheard. What does Fibonacci mean? That's just it's named after some Italian guy, Fibonacci. That's all. It has no other meaning than it's just named after the guy. So yeah, what's the complexity of this? This isn't a trick question. I'll zoom in a bit so you can see better. What's the computational complexity of this iterative method right here? Just get some water. Well, I'm not looking for you to ask me. That you put n with a question mark. I want n, period. Okay, there you go. It's n. Why? Just do the trick. Look for the loops. The loop will run, on the order of n, so nothing else. This is just constant time. These are constant time, but they're in the loop, of course, constant time. So how many times does the loop run? And it's linear. Great. So, n. And we can write this recursively. Like, this is the mathematical syntax to write the Fibonacci numbers recursively. It's 0 if n is 0. It's 1 if n is 1. But if n is greater than 1, it's Fibonacci of n minus 1 plus Fibonacci of n minus 2. That's what it is. So basically, the nth is the sum of the n minus 1th and the n minus 2th. There, I said 1th. Then take a moment and think about how this could be turned into a recursive method. So I gave you an example, but I want you to think about this without jumping right to it. Based on what you know about the factorial one, how would you write this recursively? I'll give you a second to think about what it would be. 1th and 2th. But I didn't say 1th or 2th though. I said n minus 1th. N minus 1, n minus 2. See, I didn't actually say that. I said n minus 1. You heard me wrong. Zeroth. What's wrong with zeroth? Zeroth is a word. Unless you meant to say like zerost. All right, so hopefully you spent time thinking about this and not just 1th and 2th. How would we do this? Well, okay, there's 2 base cases. If it's 0 or 1. But we can kind of, I don't know, check these base cases maybe in one shot like we did here. If n is 0 or if n is 1, just return n, right? Because if it's 0, it's 0. If it's 1, it's 1. So if it's 0 or 1, just return whatever n is. Otherwise, return what the Fibonacci number is of n minus 1. That's this part right here. Plus the Fibonacci number of n minus 2. That's this part right here. That's the recursive method. So tell me for a second. Here's the iterative Fibonacci. Here is the recursive Fibonacci. Which one, I know we ended class with this, but which one has this like this aesthetic that is just something? It's just something. The recursive, yeah, of course. The recursive one, it's not even that it's simpler. It's that, I don't know, it's beautiful to me. There's something about this right here that's beautiful. This, I don't want to look at that. You give me that, ew. And your loop's starting at 2. Oh, come on. What are you doing? I don't like this. This, oh, I know. It's just so, oh, that's so nice. It's so nice. It's beautiful. Exactly. Recursive can be like 2 lines if you really want, but actually, I guess your function definition. So, here's the problem. And when I say problem, I mean problem. What is the computational complexity of the recursive Fibonacci? So this may feel a little less straightforward compared to the factorial one we just talked about, but the idea is exactly the same. The function itself, all of the operations inside this function are constant time, except for like the fact that the recursive call is happening. So, but it really becomes a matter though of how many, if we're going to n, and then we're ending, if we're at n, and we're decreasing from n, I'm hearing n squared 1. Okay, you're guessing, that's good, but here is what I want. Stop guessing and let's think about this for a second. We're at n. We're decreasing our value of n by 1 or 2, whatever. And our base case is 0 or 1. So clearly, we're counting from n towards 0, okay? And like before, it was a matter of, well, how many times does the function get called? Well, every time I call recursive factorial, it calls recursive factorial once. Here, every time I call recursive Fibonacci, how many times do I call recursive Fibonacci? Yeah, 2 times, right? But if each time, let's think about this for a second. This call is working from n down to 0 or 1, and this call is working from n down to 0 or 1. So it's like each of the two have to do linear work. Not just this one. It's like each of the two are doing linear work. But then again, if I call like this recursive call, how many recursive calls does this one have? And this one? 2 Fibonacci times. Where did my pen go? Oh, here we go. Let's think about this pattern here for a second. If I call it here, I've got like, okay, the first call makes 2 calls. And then the next, like this call will make 2 calls, unless it's at the base case, of course. And then this one will make 2 calls. But then this one makes 2 calls. 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 And then that one makes 2 calls. 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 Then this one has 2. 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 I'm not going to keep going. The next one will have 2. That's true. Does the one have 2? Does this one have 2? Which one? The point is, we have 1 thing here, 2 things here, 4 things here, 8 things here, 16 things on this layer, 32 things on this layer. Who wants to guess how many would be in the next layer? 27. 64 is correct. Ugh. No. How many would be in the layer after that, or the level after that? 1, 28. 2, 5, 6. 5, 1, 2. 10, 24. 20, 48. And so on and so on and so on. So what is happening to the number of things? Like, what is happening to the number every time I go down? It doubles. Exactly. It doubles. So it becomes a matter of saying, okay, well, if each time I go down a layer, I double, times 2, times 2, it becomes a matter of knowing how many levels there are. And in our case, I guess there'll be n levels, because we got to go from n. At some point, in the worst case, we're going from n down to 0 or 1 by counting by 1s. Sure, over here it's counting down by 2s, but this one's first call will be counting down by 1s. So the worst case is counting down by 1s. And if we're going from n down to 0 or 1 by counting backwards by 1, how many layers will there be in that tree? Well, there'll be n, because we go n minus 1, n minus 2, n minus 3, 3, 2, 1. So we have n layers. Huh. So recursive is beautiful, but very, well, hold on. No. But I like what you're thinking. Someone's hand is up. What's up, elongated muskrat? Or was that an accident? Accident. Okay. So if I am doing like times 2, a total of n times. So if I'm doing like 2 times 2 times 2, a total of n times, how do I write that? in our nice actual math notation we use, well, we all know that that would be 2 to the power of n. 2 multiplied by itself, how many times? N times. There's n layers. So I would say, somewhere on here, that this is big O of 2 to the n. Who here knows if that's a good computational complexity or not? I'll give you a hint. It's one of the worst. Mid. Absolutely horrible. It is horrible. Exponential growth is, yeah, Will Smith is right. What did I just say? Okay. Computational complexity. Yeah. Let's see if I can find that little table. No, I guess big O notation. So, okay, here we go. Constant time. This is ordered by awesome to absolutely horrible. So we have constant, whatever, log n's, that's common-ish. N to the power of c, where c is some fraction, whatever. So that would be, yeah, whatever. N log n. N squared, n to some other constant. I mean, as we get n to the power of something, it gets pretty rough, but then we've got, I don't even know what the heck's going on here. Then we see c to the n. Exponential. Yeah, terrible. Absolutely terrible. Terrible. Arguably, the only thing worse is this factorial one. So, yeah, this c to the n, 2 to the n, absolutely horrible, okay? Why? Why is it horrible? Okay. I'm glad you asked that. Actually, oh no. I'm glad you asked, but I hope I have that. Hold on. Oh no. Hold on. Okay. All right. I'm going to read this off screen. I won't talk about why is it so bad. Like why is 2 to the n bad yet. I will in a moment. But if you were, so you might say like, well, okay, you're like the depth of that tree or the height of that tree is not actually n because, every once in a while we're doing n minus 2. This is what the tree would actually like look like if you were to do fib of 6, right? So you'd need fib of 5 and fib of 4. But fib of 5 needs fib of 4 and fib of 3. And fib of 4 needs fib of 3 and fib of 2. And so on and so on and so on. Why? So here's the thing. Why was this algorithm, which is doing Fibonacci, so bad compared to the iterative one, which is linear? If you have the option between a linear and an exponential one, you take the linear one a bajillion times first. So what's happening in this one that makes it so absolutely horrible? I'll give you a hint. If you look at this picture, you should be able to deduce what the problem is. Oh, yeah. Yeah, but that's why the algorithm is bad. But let's talk but why were we able to calculate it linearly with our iterative algorithm? Like, what is this algorithm doing logically that the linear one wasn't? Well, that's what recursion is. And I think I'll give you a hint. Let's look at this iterative one here for a second. If I said, tell me the 10th Fibonacci number. Okay, and you worked through this. I hear more boops. Ah, elongated muskrat, got it right. So, the problem is, if I tell you the iterative Fibonacci and say, calculate the 10th Fibonacci, you will calculate, well, you get the 0 in the first one for free. You'll calculate the second one once. Then based on the second one, you can calculate the third one, and so on and so on and so on. So we only need to calculate, like if we're looking for fib of 10, we only need to calculate fib of 9 once. We only need to calculate fib of 8 once. We only need to calculate fib of 7 once, and so on. But look here. For example, how many times am I calculating the fib of 2 in here? I see 1, 2, 3, 4, 5. 5 times. So this version had to do it 5 times. This version only had to do it once. And this tree grows hilariously large as n gets bigger. If I did fib of 7, here, copy. Let's see. If I want to know what fib of 7 is, okay, great. Fib of 7 is fib of 6. Okay, I'm going to do this. Okay, hold on. In fact, pay attention to what I'm doing because this is like an important pattern I want you to notice. So what I've done so far, it might be hard to see at this stage. What I've done so far is I just took from fib of 6, its fib of 5 calculation. I'm going to take all of this, there. Because in order to calculate what fib of 7, well, I need fib of 7 minus 1 and fib of 7 minus 2. Great. There. We just tacked on this giant new tree. And if we want to do fib of 8, it's going to be the exact same pattern. I'll just do, here, we can do that again. Well, we're going to need all of the fib of 6 stuff. So copy. We're going to have to calculate all of that again. Running out of room, but fib of 8. Now the tree is even worse. Right? It's not that it's being ran more than once. It's being ran a lot more than once. Artsy, thanks. Never used Q-tips. Never used, well, that's what they say. All right. So, yeah. Okay, okay, whatever. Okay, Towers of Hanoi. Okay, Towers of Hanoi. Given 3 pegs, several disks that can be added or removed from the pegs. All disks vary in size. All disks start on one peg with the largest at the bottom and the smallest at the top and are sorted accordingly. The goal is to move all disks from one peg to another with the following constraints. Only one disk can move at a time. A disk may never be placed on top of any smaller disk. And all disks must be on some peg at all times, with the exception of the one currently being moved. So you can't like just take it off and put it aside. That's this game. Who here has seen this toy before? Embarrassing that certain monkeys can do the tower better than I can. Of course you've seen this before. And here's the GIF of it happening. There is a recursive algorithm to solve this. Because the pattern to move 1 is needed in the pattern to move 2, which is needed in the pattern to move 3, and so on. We're not going to really jump into the details here. You can if you want. It's actually not that bad, but it's really tedious to explain. You kind of have to just like work through it yourself. Because think about it. If I want to move the largest disk to the end, how do I do that? Well, I got to move all of the disks smaller than it to the middle peg, then move the largest disk, then move all of the values from the middle peg onto the largest disk. Right? Extra credit assignment. Remake Tower Hanoi in Scratch. So Tower Hanoi's example of where a recursive function is beautifully succinct. Do I have an I do not. The trick is to consider that whenever we are moving a disk, there is a source peg and a destination peg and an extra peg. Additionally, what is considered the source, destination, and extra is relative to when and what disk is being moved. Equipped with this information, to move n disks from a source to a target destination, here's what we do. This is all we do. Move n minus 1 disks from the source peg to the extra peg. Let's see. I'm going to do something real silly here. Shoot. Let's fill it. Okay, we'll do... Did I not just say fill? Fill. Oh, I have to pick the fill color. Okay. So we have the large disk. Oh, God. The large disk. A not as large disk. A not as large disk. A not as large disk. And a smallest disk. Okay, great. So we are on this peg. I'm just going to draw the pegs up here just so they don't get in my way. If I want to move all of these to here, whoa, following the rules that I can only move one at a time, they have to all be on a peg, you can't have them out of order, here's all I have to do. Move all of these to the extra peg, take the largest, put it in the destination. Shoot. Let's try that again without... Okay, take the largest, put it where I actually want it to go. And then take all of the ones that are smaller than it from the extra and put it on the final destination. That's all I got to do. Now, of course, you're going to say, feels like you kind of missed some steps there because you just said, oh, move everything on top. Then move the one. Then move everything over again. Feels like cheating. Well, no. Here's why. I'm just going to move this here. Because, well, great. I have to move all of these. Let's go back here. So, when I said move all of these things to the extra, what did I really mean? Well, I mean, okay, well, move everything on top of the disk I want to go to an extra peg. Well, I'll call this the extra peg right now. Then move the disk we actually want here, the biggest one that we're moving, to the extra peg. Or sorry, the destination peg. And then we take the things on top of it and put it back. But then you're saying to yourself, well, I mean, hold on a second. You just said move everything on. Well, okay, fine. We're going to move this here. Then move this here. Then move this here. Then I'm good to move this where I need it to go, right? But then, of course, you go like, well, okay, well, how do you get that other thing? Well, okay, I'll move that there, that there, and then that there. Then this can go where I needed it to go, which was, oh, I think I put these out of order. Well, whatever. My destination pegs have changed. Not too important. So now I can put this where I need it to go. Now I got to put these things back, though. Okay, so I'll put this on the extra. Put this here. Put this here. Put this here. This can go where it needs to go. This can go here. This can go here. This can go here. Nope. This goes here. Nope. This goes here. Well, now I'm doing something wrong, but I clearly got out of whack. That's the idea. There's a pattern to this. So when I say, oh, move everything on top over, I'm kind of speaking recursively. How do you move the things above? Well, do it recursively. So all I have to do is move the n-1 disk from the source peg to the extra peg, move the nth disk to the destination peg, and then move the n-1 disk from the extra peg to the destination peg. Steps 1 and 3 may feel like cheating, but notice that they are actually recursive calls. Also, what one considers the source and destination peg will change when moving the n-1 disks. Okay, looking at the first step, I say move n-1 disk from the source to the extra peg. Okay, how do we do that? Well, move the n-1 disks from the source peg to the extra peg. Then move the n-1th disk to the source, from the source to the destination. Then move the n-1 disk from the extra peg to the destination. Well, how do you do that? Well, you move the n-1 disks from its source to its destination. Then you do the n-1 to its destination. Then you do the n-1 to the destination. And so on and so on and so on until you're at the base case, which is move the one disk. Anyways, this is a non-trivial problem and algorithm. And if you're struggling with these ideas, don't worry too much. I really just like to talk about this example because there is this right here is the recursive algorithm. Let's see if I can find an actual implementation to show you. Yeah, here we go. If it's size 1, this is the base case. Otherwise, move a-1 from 2, and then the extra. Then move the 1, and then move the a-1 from the extra to the destination. Yeah, I think so. Pretty sure it is, at least. Fairly certain. They just outed. They didn't actually do the change, it looks like, which is strange. But, oh yeah, because that's what, okay. So that's pretty cool. It's a very simple algorithm. An iterative version is ugly. Now, I will say, so someone made a comment saying oh, okay, so recursion is simpler here, but recursion is just way slower computationally. This algorithm, we could write a recursive Fibonacci that's linear time. You can totally do that, but it's not as beautiful as this one is. So, yeah. You can do this with something called dynamic programming pretty easily, but okay. Only thing I remember other than Scratch from high school programming, a C++ syntax was a pain. Yeah, I agree. So now I want to tell you the story. So where's the, okay. All right, so here's the legend. I'm reading on another monitor, so you're going to see me look away. Numerous with regard, okay. Okay, so. Okay, so here it is. There is a, okay. There is an ancient temple somewhere in India that contains a giant room. And this is a very holy place. It contains a giant room with 3 time-worn posts. Okay? And one of them is surrounded by 64 golden plates. But the plates have like a hole in the middle, so they can go on these pegs. But these posts that are time-worn are kind of like very special, important, because the plates are exceptionally fragile. All right? So these plates will break if they are ever placed on any surface unless that surface is contained around that post. Okay? So these plates, they can only ever exist by like around these posts. And of course, we can never put a small plate on or a big plate on top of a small plate. It'll break the plate. And these plates are very important. Okay? I cannot get this across enough. So acting out the command of an ancient prophecy, there are monks that have been moving these discs in accordance with the immutable rules since time began. I heard some questions. They're magical, yes. Since time began. So, the interesting thing, though, is this holy place is once the algorithms that these monks are executing, because you figure these monks need to move these plates. Okay, the 64 plates from the destination to the target. There's 3 sacred posts. But here's the thing. It is said that once the monks finish moving all 64 plates, 64 is not even a lot, right? But once the monks are done moving all 64 plates to the destination, the universe ends. That's it. That's it. And it's interesting because the monks are moving these plates in a systematic way. They have to follow the rules that we have, Towers of Hanoi rule, where, they can only you can only move one at a time. They're really fragile. Bigger plates can't go on top of smaller plates. And they can only, they have to be on a post unless it's the one being moved. There's only 64 of them. And it's kind of interesting because the monks will be following, that recursive algorithm. It's just, they are the computer executing this task, right, of moving the plates. But it's kind of funny to think of the humans executing that algorithm, but they would totally be executing the algorithm. It's the same algorithm. It's just, right? So, the universe is going to end once they move these 64 plates. Now, these monks have been doing it for a very long time. They're kind of like demigods or something because they're living forever. And they can move at a really rapid pace. And they're really good at it now. They're a very well-oiled machine. So these monks can move a disk, like one step of okay, I got to move this plate to that peg, right? They can do that. They can move one plate to a different peg once a second. All right? Once a second. Okay. So, I guess it'll just take 2 to the 64 seconds, because if they've got to move all of those plates, it's 2 to the 64. So if we can do it once a second, 2 to 64. Well, what is 2 to the power of 64? Oh boy. So that's seconds. Okay, so let's divide that by 60 for minutes, and then divide that by 60 seconds per minute, 60 minutes per hour. And then we'll divide that by 24 hours. So how many days? a lot of days. All right, so that's how much, 24 hours, 365. I'm not going to do the leap year. So how many years? So this will tell me how many years. I mean, we're okay. Okay, that's how many years. How many centuries? So divide that by 100. All right, you know what? I give up. That's a long time. Let's get rid of the 100 years. How many years is that? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2. Okay, wait. 1, 2, 3. That's the billion. 584 billion, 942,417,355 years. How long has the universe existed? Someone look that up here real quick. How old is the universe? Come on, you guys don't even know that off by heart? Come on. It's about 14 billion years. Oh. I think it's at least since 2002. Oh, I understand. You were born in 2002? Whoa. 14, so let's call it, it's 14, it's 13.8. Let's call it 14. 14 billion years. All right, fine. Minus 14 billion. Million. Okay, great. It's still gonna, the monk still got 570, almost 571 billion years to go. These monks just got started, I guess, because they're nowhere near done. That's moving once a second. Once a second. I could divide this by 1,000 and be like, okay, that's once a millisecond. And it's still going to be an insane number. Okay, it's going to be 500 million years if they do it once every millisecond. What do they do that every nanosecond? Microsecond? Okay, 584 years if they can move them a microsecond. And if they can do it in a picosecond, well, they can do it in about half a year. Which is insane. Exponential growth sucks, okay? Exponential growth gets out of control fast. There's only 64 plates. Only 64. That's not even a crazy big number. If you didn't have to follow the rules, you could move those plates into, if you didn't have to follow those rules and you can move one plate a second, it would take you 64 seconds. Can that problem be solved a different way? I don't know, you tell me. Call the Flash to help then. Can the Flash move at the order of picoseconds though? I don't know. All right, well, we heard it from, we heard it, all right, horse's mouth, I guess. Okay, nice. An attosecond, if that means, all right. I don't even know what an attosecond is next to a pico. I'm getting it's smaller, obviously, but. All right, let's see. What? Pico, okay, atto times 10 to the negative 18. There you go. Top 10 numbers. 10.4, 9.5, 8. I'm not sure. 1/1. Sure. Point being, exponential growth is terrible. So let's take this back to Fibonacci right before we end up. If you have an algorithm that if you wanted to calculate, let's say you were capable of calculating the nth Fibonacci number once a second. If you wanted to calculate the 64th Fibonacci number, would you use the iterative one, which is linear time? And if it's linear time, it's going to take you about 64 seconds because, you know, 1 a second, you got to move all 64 of them. Or would you come back in 500 whatever billion years? Which one are you going to pick? obviously the linear one. But this puts in perspective how much different a linear time algorithm is versus a exponential. There are a lot of problems out there, though, that require this type of stuff. And this is where a lot of like AI comes in. Could my laptop do it? Give it a go. See what happens. TSP. Here. You know what? We're out of time, so leave if you gotta leave. But I'm gonna do the recursive Fibonacci here real quick. Okay. Oh, so rec fib. Nope. FIB. Nope. IB. Okay. So if n equals 0 or n equals 1, return n. Else it'll be a return rec fib of n minus 1 plus rec fib of n minus 2. All right. How do I do timing? I'm going to do a quick thing here. Time difference time Java. I can never remember how to do it. Every language is a little different. Start. Okay, cool. Okay. Start. Okay, so I'm going to do, let's calculate the 10th Fibonacci number. And I'm going to s out elapsed time. Basically what I'm going to do is I'm going to call recursive Fibonacci. And I'm going to calculate how long it took the computer to run it to 10. Will this be on YouTube? Yeah, this part's still recording. So let's hit run and see what happens. $55, and I think it's probably in milliseconds. Yeah, time in milliseconds. So it took 55 milliseconds to calculate the 10th. Great. All right. Well, let's try the 11th. Just one more. How much more work could it be? Oh wait. No, that can't be right. 55 was the nth Fibonacci number. Oh no. Did it make it iterative? Oh no. I'm wondering if the compiler has actually turned this iterative for me, so I actually can't get a sense of how long it takes. Crap. No, it's ruining the fun. It probably most certainly. Shoot, let's see. Okay, oh, maybe not. I'm calculating the 100th. Okay, I'm going to stop doing that. Let's calculate the 20th. Maybe it wasn't. Maybe it wasn't. I just need to get to a bigger number. So the 20th Fibonacci number is that it took about 1 millisecond. Okay, let's do the 50th. It's still going. I mean, I can... It's running. Getting kind of impatient here. Come on. I mean, should I let it keep running or should I stop and try a smaller number? What do you want? No, it didn't crash. It's still running. I can see it's running just fine. Keep your fire extinguisher. Nah, don't worry. Come back in a few years. I mean, that's the thing. I don't know. Let's stop that for a second. So I did 20. Well, let's just see what happens with 30. 20 was okay, right? Okay, 30. It took 7 milliseconds for 30. Okay, 35? 56 milliseconds. Okay. But I mean, 7 to 56, that grew pretty quickly. see with 40. 40 took, ooh, half a second for 40. 41. 0.8. Over a second for 42. Let's see what 45 is. Five seconds. Jeez. It's 46. I mean, I'm starting to get a sense. Maybe it would have taken a little while if I was trying to get to N is 50. Keep it. 46 took 8.5. Doesn't seem too bad. 47. That's like a minute for 50. Well, I don't know. We'll see. How much is 47? It's still running. $13 seconds. 48. I mean, we get the idea. Anyways. Now think of like, oh, but what if you could just do it in linear time? I mean, this would be done in like 0 milliseconds for this computer. Anyways, we'll end there because I am way over time. But yeah.